Okay. Hello and good afternoon, everybody. To the webcast Cooperative Intelligent Transportation System and how it's supported by Lisa and what was the updates in the last half year. So let's have a small introduction. Hopefully it works. It works right now. What's the reason for connected and automated vehicles right now? The reason is in first place, it's safety, increasing safety on the roads. Next part is the increasing of the comfort and of course for overall the increasing of the efficiency of the whole traffic system. This is the reason why we connected and then automated vehicles here. It's a nice abbreviation here. CAV means the connected and automated vehicles. And what we're seeing so far is that we have very intelligent vehicles which can determine the current traffic scenario very well. And what we're gonna do or what we would profit from is that we exchange the information, do it in a more in a more cooperated way, so that the infrastructure can a bit more intelligent too. That's the reason why we develop CITS functions from an infrastructure point of view. So let's move on. The current trend is, of course, we have a V2X communication here, and today I don't want to talk about the communication technologies there are. We have a dedicated short-range communication, we have cellular networks, and so on, and it's increasing the ways how information gets into the car or from the infrastructure to the vehicles. Let's talk a bit more about the messages or the information which is exchanged between each other. On the one side, on the vehicle side, we have currently the CAM message. It stands for a cooperative awareness message, and it's like a floating car information. So you will get the current position, the current velocity, the priority, the type of the car, um, also information about in cases of public transport, of the course and the route of the vehicle, and so on. This information is very, very fine to track a vehicle in front of a connected device like an onboard unit. The next part of the information exchange is the so-called SRM. It stands for a signal request message, and the response to that is the SSM, the signal state message. This is especially for the public transport sector and also for the emergency sector, because here you can give a request to a specific signal group that you will pass the intersection, especially with that route, and so you want to have green for a specific, especially that signal group here, and you get also a response, so you can bring it directly to a trajectory of the car. And next, we have the infrastructure side. And from the infrastructure side, hopefully you see my pointer here, um, you have to provide some information back to the car. And on the first place, this is information. It's a map message. It's information about the topology of the intersection the car will pass. Though that information is very static and includes the ingress and egress lanes, the possible connections in the intersection, the restrictions, the signal group. It's all georeferenced, speed limits, traffic signs, and so on. This message is the base for the next message. It's a so-called SPAT message, which is an abbreviation for signal phase and timing. So if you want to interpret the current signal state in the car, like red or green, then you need both messages. One for the topology, so you see the signal group and the responsible connections, and next the information of the SPAT. You need both to optimize your trajectory here. And in that SPAT message, the current signal state is included. And of course, with more and more traffic actuated signal logics, which means that we have some variables in there. So there is values for the shortest uh, the, the the shortest end of a single phase. That's the min, the max time, and of course, if you have a good prediction, you can give also a likely time. The likely time wants to show up the correct switching point in the time range. Then you have the next signal state and so on. but this is an optional information. I will come to that later on. Next, let's see a closer look to the dedicated short-range communication, which typically uses 11.p, a Wi-Fi communication standard. Here is the topology that way that we have, of course, the traffic light controller with a connected RSU as one unit, which is able to broadcast some information like the SPAT and the map message. Next, we have a receiver. This is, of course, our vehicle, which receives that information, and together with the own position of the car, it can match it, do a map matching based on the GPS location, and then have the correct signal information in the car. This is necessary because nowadays vehicles are not able to detect by our image recognition the the signal state 100% correctly. So this is really needed right now to have a very safe driving also with automated cars. And of course, you can, based on that information exchange here, you can have some services like a Glosa, a Greenlight Optimal, or optimized speed advisory, where the goal is to optimize the driving strategy, which means in cases of a fuel consumption and also for the driving comfort. Because if you have more knowledge than the other drivers around you, I think this is very positive for yourself and your driving procedure here. Um, Next, okay, there are some issues here. First of all, we think that a traffic light forecast is very essential for a spot message. It's not only the current state, it's also the upcoming state of the faces, signal faces out there. And of course, as I already said, we have a map which is related to the connections in the intersection. If you have some changes in there, like roadworks or another update of the whole intersection, you have to update the map too, because otherwise we get some problems with the vehicle. And next, of course, right now the Glosa services up here, it's part of the infotainment of the car. So if you want to have it in an automated car where we have really high restrictions, you have to be really sure that the safety and security issues are all solved. To give an example how connected and automated cars influences the capacity of the road network, I have a very tiny example here. So let's have first look. This is the conventional driving strategy at a signalized intersection. You see you have the cars, and then you have some times for the driver to react. This is done by humans. The possibility to react to the different traffic scenarios. And by changing that to a platoon of automated cars, you can have this really a nice little example, but you see the effect here. And you see by connecting and bringing the sensor information together, you have really slow, really low times to overpass the stop line here. So I would go next, and state of the art in the cases of traffic management, especially in the area of traffic light signals, we have a high quality traffic light signal controls algorithms available. This we can do have a comparison of different traffic streams in multiple traffic light phases. We can have a request for all the single traffic streams. We do the computation of green times in single seconds, which means we are really traffic actuated and accurate to the current traffic flow. We have a prioritization for the public transport as well, at the coordination of arterial roads and networks which means it's a macroscopic point of view. So I think, in my opinion, the current state in the area of traffic management is really high, but it can be also increased by using new technologies and new information. So if you have a look to the current state of the art, how you determine a specific traffic scenario, you will see that most of the time you're using loops, induction loops, or detectors, which is located at a specific place in your network. That means you can only have information about the demand or the occupation at a specific point in your network, and all the other things you have to do is an assumption. You have made assumptions. How many cars are next to the loop or behind, or how many cars are moving towards my stop line and so on. And we think if we have connected driving here and we have information exchange, especially to the traffic lights here, we have information exchange between the vehicle and the infrastructure, and also infrastructure to infrastructure. Let's share their information and do a better traffic experience here. So what we want to have is not a discrete measurement, we want to have a continuous measurement and to complete the detection over all vehicles. So we have the best view of the current traffic scenario and can react as good as we can. So let's have a closer look to the other way, to the reverse way. We have the vehicle here, which is able to share the position in order in the way it provides CAM messages, cooperative awareness messages, including the position, the time, and the velocity of the car, and much more information. This can be transmitted directly to RSU. It is broadcasted, so traffic light with including RSU can receive that information. Together with the map M, there could be a map matching. So you have direct the information on that lane or that approach. You have so many cars with that distance to the stop line, that velocity, and maybe also the waiting and the time loss values here. So you can provide that information additional to the conventional detectors. That's the idea behind. And so you can increase the quality of your actuated logic. And of course, the map information needs to be managed and maintained, of course, because you have changes in your network and you have to take care that you can map match all the vehicles correctly. To do this in with the tool Lisa, with the traffic management tool, the traffic tool Lisa, there is an export for that so-called and standardized map messages. This is done during the planning process. We think this is a good idea because if you plan and signal light, you have all the information. You have the position of the signal groups. You have all the incoming and outgoing coming lanes. You have a high accuracy because you write your control next to that information. So I think it's a very good idea to export directly that map information out of that information source. Another very important point is we can also have multiple signal groups for a specific connection, which means we can have a primary and also a secondary signal group. And by providing spot information to the vehicles, you don't bring in the first line the signal state information. You give a movement state to the vehicles, because for a vehicle it's very important to see, can I go or should I stop? And it's not the information about the signal light itself. This is important to know here. And of course, we have tools like Google Earth where you can see the accuracy of the network you've done here. So this is one thing. The next thing is if we have cars out there or vehicles overall, which are able to provide information in a way I showed up, like the CAM messages, we get a list, or in our opinion, a list of vehicles would be very fine, which means we have a map matched car on a specific lane, a specific vehicle type, also aggregated information like the distance to a specific stop line, which is part of the map message, the current velocity, the priority, and a bit more information here. And with that kind of information source, or like a table with different rows, we can develop a lot of new functions. A lot of functions which can be included during the planning process of a traffic light. So in order to see where we have some tiny gaps in our current controls, I have two examples here. The first is the requirements for green time computation. So currently we are using induction loops to determine if there's a occupation for a specific lane or not, which means we can only see the occupation if the car stands directly on the detector or in the detection field if you have camera detection here. So we can use that, and even at low traffic demand, the problem is the car has to go onto the loop, and only then I can do a decision here because I have no other measurement points here in the network. So even at low traffic demands, we have maybe long waiting times here, and that cannot be avoided. It's during the measurement itself, and V2X technologies can solve that problem. And the next point is that we have interruption using a time gap criteria. In Germany, it's famous to use time gap criteria, which means you have an induction loop, which is around 2 or 3 seconds before the stop line. And then you can measure the gap between two vehicles and interrupt the green phase if you see that that gap is increasing. So you see that the platoon ends and there's no other cars on the road. So platoons can hardly be recognized by current detector types. This is just part of the measurement here. So we cannot extend for huge platoons, which are on the way, but wasn't recognized by the detector itself. So let's see how V2X technology can solve exactly that problems here. The first, it was the V2X request of a signal phase. So see if if there is a request of a car. So in first place, you can do using the conventional occupancy detectors right to the stop lines, which means we have it's the K1L signal group here, and we have a car. The request is at time 0. Then we have the request. We see the car here, and then we will change to green, but waiting for the phase transition for the other phases, which means we have a waiting time around 10 seconds here, and here the green begins. To avoid that, you can also use the loop for the time gap criteria, which is much above which is 30 meters away from the stop line. So you can use it. And what's the deal here? You have the request 3 seconds before it's reaching the stop line here. So you can have the arrival here and what's the name? Decrease the waiting time for the car. Now the car only waits. The arrival is here. I think it's around 6 seconds here. We have a waiting time around 6 seconds. By using V2X technologies, we can have the request as far as we have we receive the information of the cam messages during the ride here. So if we see the car, let's say 12 seconds before the estimated time of arrival at the stop line, we can react directly. We have the request here, which is red. Bring the green here, and we have the arrival directly after the red amber phase here. So the car will directly move. For the driver, it would be great to have a spot information also that he had the information that he can have that velocity unchanged here because it's really short here for the switch. Next, we have the extension of a signal phase regarding platoons, which is far away from the stop line. And the idea here, or one of the idea here, is to have an additional factor. The additional factor is a mean extension requirement per vehicle. That means here the green rectangles here are connected vehicles. So in a specific range, around 12 seconds before a possible switch, we are counting the vehicle, the communicating vehicles in that area. And in that case, we have 5 vehicles here. So divided by the 12 seconds left, which we have in our traffic light logic, we have a mean extension around 2.4 seconds. And this is below a specific threshold in the logic. And by using this, you will extend your green window because you've noticed that there are cars on the road there. Next time, we have the same situation here, but not all vehicles are equipped with communication technologies. So what we have here, same procedure, 12 seconds, only 3 equipped vehicles. We don't care about the other vehicles here, and we see that our threshold here, our value here is the mean extension. It's around 4 seconds, which is upper than our threshold, which means there is no car-to-X green extensions. The result here is we have a conventional control using new technologies, but The equipment, we don't care about the equipment rate. If the equipment rate is high enough, they can profit from that. If it's low enough, it's just the fallback is the conventional control here. Though it doesn't matter how big the penetration rate is. But as we have equipped vehicles, as better can we determine the current traffic scenario here. That's the idea here. Of course, there are some new ideas here, much more ideas. First of all, the main rule is unused green time is additional waiting time for the other direction. This is, I think this is clear. With CAR-TX information, we can have an efficient distribution of green times. So the estimated time of arrival at the stop line, or the demand, the volumes, the waiting time, the time of time losses on the road, and so on. All that can be measured by tracking the cars. Care messages can also be broadcasted by pedestrian and bicycles too, because we want to measure all the participants at an intersection, not only one specific equipped vehicles right now. We have here, of course, traffic jam management in overload situations is really an issue because conventional detectors cannot measure that. You need video cameras at specific locations and so on, very, very long loops to detect that. Cam messages can have a really big benefit here. And of course, from our point of view, the usage of V2X information is more an evolution than a revolution, because we are using existing ideas, existing logics here, and extend that with that new information. Let's come closer to Lisa right now. In Lisa, we implemented some new control methods regarding the map, the SPAT, and the CAM message. For the cars, we have now an interpretation of the CAM messages, which are received from an RSU. So you can use it to determine the traffic demand, you can see platoons and so on. And we implement very, very basic functions because we think the user should have a really good possibility to include own strategies, own ideas by using exactly that values. So we have a couple of new, very simple functions which you can bring together to have a really sophisticated logic itself. Nevertheless, we will provide much more aggregated functions where we put in some more sophisticated logics based on that basic functions we have here. And the mention goes on and on and on. This is for the CAM messages, where you can see you have a list of all the cars. This is here, it's a count. You have a specific ID for every vehicle. You can see the length, the deceleration movement, the acceleration, which is the approach of the car, and so on and so on. Next, you have also the information which comes up from the map message, which means in your current logic, you have now the possibility to see how many lanes I have, what's the connections from lane to signal groups, and also you see all the restrictions. You see which car is on which specific lane and what is the responsible signal group to that. This is all the information you have, and you can build up really cool logics in with that functions. And of course, during the last day, we have a real implementation exactly with that methods here with a Swarco traffic light controller. It's called Actros, and ELISA control, which acts together. So you have an information exchange between the RSU. You get the information. You can use it directly in a traffic light logic. Next, I will provide you a structure. Sorry, a structure to see how you can implement it in Lisa. This is your current control. I will explain it. This is for the time gap criteria. That CL, that abbreviation here, is a function which computes the time gap for a specific detector. The detector is called D2_1. And if this value is above a specific threshold, the threshold is this, you will stop that green phase for that direction. So the value for the for that is here is true. So you avoid the green here. And now we have a next condition. So if you see that the time gap criteria is fulfilled, and then to also check if there are some cars on that approach here. So on approach 4, iterate over all the vehicles which is on the road or which is equipped and on the road here. And if you see that there's a vehicle with an estimated time of arrival below 5 seconds, you will deny the cancellation of the green window. So you set that value to false. So what we done here was it's just an extension of a real time gap control by using new V2X technologies here. Okay, next I will come to another message type. Message type now is the SPATEM, the traffic light forecast. In Lisa, we want to provide also next to the current traffic state, we want to also have a prediction for the signal states of our very complex and traffic actuated traffic light logic. For that, the idea is to have a local prediction in first place. This means the forecast is directly included in the traffic light logic itself. This is just an addition to the traffic light logic, which means it's more than a function call. I would call it like that, which means we have during the traffic light logic in the controller itself, we have access to all the relevant control map parameters. We see the current state. We have opportunity to use all the methods, which is also in the traffic light controller, so we get really good decision making variables and states here. Next, with that approach, you don't have latencies for the prediction, which means during the run of your traffic light logic, where you compute all the switches, which goes directly to the control, you have all the information for the prediction before that information about the switching is go to the controller itself, which is great. So there's no latencies in the system. There's no need for an external device because it's running directly on the traffic light controller, and you have a recomputation or an update every second. And maybe even lower. So you will, for highly actuated controls, it's really important to do that. And it's working directly after the installation of the logic. So to get a feeling how this works is, our traffic light logic is known in Lisa. It's not known how complex you build up your signal programs, but the logic itself, it's known. So you see all the decisions, the restraints, and the thresholds, which is in there. You see the dynamic variables. You see also the constants, the signal time, the frames, and phases. But during the runtime of the control, you will see the internal variables states. You see all the input values, the detectors, the public transport, the control method parameters, which is exchanged with a traffic management central, for example. So this is great to have if you have a locally, you do the traffic light forecast locally. In Lisa itself, to have an evaluation or a test before you bring it to the controller, we implemented a traffic light forecast directly to it's called test plots. It's a test suite included in Lisa. So what you're going to do is write down your signal program, bring in some traffic scenarios by defining demand, defining specific scenarios, maybe with public transport and so on. Then click on a button which is called traffic light forecast. Then it takes around 30 till 60 seconds, and then you get an overview how good your prediction can be if you provide that to a real traffic light logic. This is cool because you can check the prediction accuracy during the planning process and not when it's outside. So you get a first impression how good it will be. So next I will talk about the task for the future. So from my point of view, the requirements for traffic engineers in the future are the complex traffic light logics as we know it now won't be replaced. They will be extended, of course, and they will bring in some new ideas, but I don't think they will be replaced so far in the future. The generation of map information will be a standard in the planning process. I think this is clear. Um, we think that the forecast component is very important extension for traffic light logic because you can implement it. It's just like a function call, and you can provide some information for a RSU, for a central, for whatever. And people can write tools or apps or whatever to show that information. Next, we have the planning of communication devices will be important. Of course, you need if you want to use communication, you have to take care the sender and then the receiver can exchange information in a good way. Line of sight could be the best here. Of course, in the future, we will have increasing information, more data, and so on. So it should be efficiently managed. On the infrastructure side, you can use dedicated short-range communication. So you have to take care that you implement such devices here with specific firmware and a good information exchange. We can also use things like cellular networks, like the famous 5G network right now, or 6G or whatever. And next, and this is really important, you need, of course, equipped vehicles. That means you have to take care that they are using standardized communication units because of the protocols and so on. And also they should provide CAN messages. So we can have intelligent cars and also an intelligent infrastructure. So in my summary, our V2X technologies are actively part of different R&D projects, mostly in Germany here. We build up a real-time communication between the traffic light controller and the RSU to exchange very, very fast the information of the equipped cars, the received CAN messages. A very important point is the integration of that V2X information in the traffic light logic are not done via a detector or input or a user variable or something like that. It's information with a specific format, which is really, really flexible and really extendable. And of course, we have currently support for the public transport container in the CAN messages itself to see the effect and to respect that in the logic. So now I'm at the end of my presentation, and let's have a look to the upcoming events. This is at least a click along webcast I see here. It's also free by Torben Tietzer. Next, a webcast to the tool for traffic analysis and so on. It's also done by Torben Tietzer. Next, there's an intelligent net control, which means it's a macroscopic traffic management, which is done by myself. It's called Unused. It's a tool of Schlotter and Bauer. And next we have also the LISA courses here, the regular online training and an extended one, the advanced one here. So now I'm at the end and I'm ready for the questions.
Thanks, Mario, for this great overview. In chat, we don't have any questions for now.
Okay.
But if anybody has a question, they can raise their hands, or you can always write to us if you have. Oh, there are questions here, we see. So there's a question from, so first I'll go with Rafael, Mr. Rafael.
Can you read it?
No, I mean, he has raised his.
Yes.
Yeah.
Okay.
I want to know this communication between the modem and the traffic light is
Yeah.
supported 100% by the traffic light, or do you have like a middleware to communicate to the radios? It's good to know because today a lot of companies are providing like a middleware, so you transfer the computation power from the traffic light to this middleware, or this middleware sends to the modems. If you have like in one place, it would be much better. So that's why I'm asking about this, how they set up this build it.
Yeah. The RSU, as I named it, the roadside unit, it's not only a modem, it's also a tiny computer in there. So I've showed up, but there's a map matching process here. You get the position, need the map, and map matched it together. This is done by the RSU unit, which means that that kind of middleware you're talking about, it's part of the RSU right now. So the traffic light signal can have only a tiny processor, I would call it like that. We don't have the power to do a much more sophisticated things. But this is done already by the RSU. The table I showed on one of the first slides, this is the information we exchange directly with the RSU. It's pre-processed data, right?
Okay, good. Thank you very much.
Great. There's also one question from Mr. Falk. Yeah, you can.
Can you read it? I have some troubles
No,
here.
no, no, no,
to
no, no.
the
I
comments.
mean, there's no question written here. He's just raising
Okay.
his hand, so he can ask
Okay.
now. Mr. Fall, we cannot hear you if you're asking something. No, we don't hear you. In case you have question, you can also write to us.
What I really like at the idea of integration of CITS components at the point that we can use an existing traffic light logic, put in some hardware like communication devices and so on, and let's have some new functions in our already existing environment here. So this is really cool for the planner because he can use it by default. He don't have to be a very electronical expert or something. Yeah, we can bring up some really easy to use functions here, which he can include directly or she in their logic.
Mr. Phil, do you have one more question? I see you raise your hand.
Yes, yes, a very good presentation. There's I have so many questions. Is about to collect the car the CAN message. Is possible to collect and transmit to the surveillance system, or this information is just available in the controller side?
Mm, there are more than one answer to that question. First of all, the information exchange for the CAN messages. Firstly, it's for vehicle-to-vehicle communication. But you can, because it's a broadcast, you can receive it directly with a let's call it a roadside unit, which is out there, and we use the possibility to transmit that info. You pre-process the data and transmit it directly to the controller, but you can also transmit that information back to a traffic management central or whatever service. But you have a little bit to take care about the security of all the things because you have something like an ID in that CAN messages. Maybe this is a reason. You have this is a rule where you have to think about that. But the possibility
Okay,
is here, of course.
thank you
Can
very
exchange
much.
that information. Yeah. Are there any
Great.
other
No,
questions?
Mario.
No?
There are
Okay.
nothing in the chat, but if somebody has any question, please raise your hand, or you can also write to us anytime. We'll be happy to answer. Okay.
Well, maybe some last words. If you enjoyed that presentation and have a lot of upcoming ideas, what you want to do in the future and what you would like to see on the infrastructure side, let's call it that way, and you have some requirements, what you especially need, feel free to ask us or just give us a hint. There's a requirement. We need that. So we can use it in simulation, test it if it's really a matter or not. So feel free to give us some feedback here.
There's one more question from Mr. Rune.
Sorry, just one last question. Is it possible through the CAM message to report the routing of the vehicle to
Perfect
avoid
question.
like false detections? Let's say that you actually want to go left and then you actually detect or extend the green light phase for the through going traffic.
Yeah,
Is it
absolutely great question. Yeah, this is a really a challenge. Okay, let's give two answers here. The first answer is if you have routing information in the car, which is great because you have a navigation device which has the routes. Typically, a car doesn't know where it will go. So if you had that specific route information, the only message I know so far is the SRM, the signal request message, because if you know your route and have the map message, and no, if you know your route and you have your map message, you know exactly which signal group you will use during your ride. So you can especially give information to the traffic light which signal group should go next green. But this SRM message is only for the public transport and the emergency vehicles. So next, if we are really precise in locating the vehicles, so we can see the lane which the car is standing on, next to the traffic light, we know which signal group is responsible to that especially lane, but not 300 meters away from the intersection. I think we need more extended messages here, or maybe another information channel. I talked about we have standardized messages like the CAM messages, but we can also, or you can also include more information messages here and bring it. You have to take care to bring it directly to the traffic light controller, and then you have all the methods I've shown so far.
a small thing to add to this point. Remember, Mario, we had this discussion about in
Yeah.
future using the car indicators
Yep.
to be included to know where the vehicle will turn or go straight.
Yeah.
Yeah.
There are some ideas during that fact. To me, it comes in mind that we have the most probable path approach, where you're doing some assumptions where the car would go. So you see a little, maybe by factors of the intersections of the transition metrics and so on.
There's also a suggestion or comment from Mr. Evangelos in the chat that maybe MCM will include this information in the
Yeah.
future.
Yeah, right. But this is currently not supported here. Yeah, you're right. The maneuvers is would be great to have it here, and I think it would be a good interaction between the traffic light logic and that MCM messages here. To exchange maneuvers with the cars, I think this could be a really good, great chance to optimize the overall traffic at intersections, right?
I think we can conclude, Mario.
Okay.
And if you have any questions, please write to us on at the ID you see here, service@slowtower.de, and we will be glad to answer. And also, as Mario said, if there are any requirement suggestions, yeah, just feel free to contact us.
Okay. Thank you very much, and yeah, see you later.
Thank you. Bye bye.